Look up at the night sky. What do you see? A scattering of stars, perhaps the faint glow of a distant planet, or the soft arc of the Milky Way. But beyond that glittering curtain lies something far more bewildering, an unimaginable expanse of emptiness, silence, and questions we still can't answer. The cosmic void isn't just empty space. It's a canvas of mysteries, each one more puzzling than the last. What lurks in those endless stretches of darkness? Why does the universe behave in ways that defy everything we think we know? And perhaps most haunting of all, are we truly alone in this vast, echoing abyss? This is a journey into the unknown, where the rules of physics twist into paradoxes and the very fabric of reality seems to unravel. We're about to explore 25 of the universe's deepest enigmas, phenomena so strange they sound like science fiction, yet they're undeniably real. From black holes that shouldn't exist to galaxies vanishing without a trace, from whispers of parallel dimensions to the chilling possibility that our entire cosmos might be a hologram. These aren't just curiosities, they're clues to understanding the true nature of existence itself, and every answer we uncover only leads to more breathtaking questions. So consider this your invitation to step beyond the edge of the known, to stare into the void and dare to ask, what if? Because the universe isn't just a collection of stars and planets, it's a living, breathing mystery, and we're only beginning to scratch the surface. Buckle up, by the time we're done, the night sky will never look the same to you again. Imagine if something made up more than a quarter of everything around you, yet you couldn't see it, touch it, or even prove it exists. That's the maddening puzzle of dark matter, the universe's most elusive ghost. We know it's there because galaxies spin faster than they should, and light bends in ways that defy the laws of gravity as we understand them. The math doesn't lie, there's something massive out there tugging at the cosmos. But what? For decades, scientists have chased shadows, proposing particles like WIMP, weakly interacting massive particles, that might flit through our bodies by the trillions without us ever noticing. Others point to actions, hypothetical particles so lightweight they'd slip through detectors like mist through a sieve, but so far no experiment has caught them in the act. Projects like the LUX Zeppelin detector, buried deep underground to shield it from cosmic noise, listen for the faintest whisper of a dark matter collision. The silence is deafening. What makes this mystery so unsettling is the sheer scale of our ignorance. Dark matter doesn't just nudge stars, it sculpts the universe's very skeleton, weaving the cosmic web that galaxies cling to. Without it, the night sky would look utterly different, and yet we're left grasping at theories that feel more like science fiction. Could dark matter be evidence of an entirely new physics, a hidden layer of reality we've barely begun to comprehend? The more we search, the more the void seems to whisper back, you're missing something fundamental. One thing's certain, this isn't just a gap in our knowledge. It's a chasm, and crossing it might rewrite everything we thought we knew about existence itself. If dark matter is the universe's invisible scaffolding, dark energy is the shadowy force tearing it apart. Picture this: not only is the cosmos expanding, but that expansion is accelerating, as if some unseen hand is pressing harder on the gas pedal with every passing second. Astronomers stumbled onto this mind-bending revelation in the late 1990s while studying distant supernovas. These cosmic beacons, which should have dimmed with time, were fainter than expected, proof that space itself was stretching faster than anyone had predicted. The culprit, a mysterious repulsive force we now call dark energy, making up a staggering 68% of the universe's total energy. But what is it? Einstein's old cosmological constant, a term he once called his greatest blunder, has resurfaced as a leading theory. It suggests that empty space isn't truly empty but seethes with a latent energy that pushes galaxies apart. Other ideas point to phantom fields or even flaws in our understanding of gravity itself. The most unsettling possibility: dark energy might grow stronger over time, leading to a Big Rip scenario where it overpowers every force in nature, shredding atoms and space-time itself in a catastrophic finale. The evidence is etched into the afterglow of the Big Bang, the cosmic microwave background where faint temperature fluctuations reveal dark energy's fingerprints. Yet for all its dominance, we're no closer to understanding its true nature. Is it a property of the vacuum or something far stranger? Every telescope, from the James Webb to future missions like Euclid, is hunting for answers. But one thing's clear: dark energy isn't just shaping the universe's fate. It's rewriting the rules of reality as we know them. Picture our galaxy, the Milky Way, racing through space at a staggering 14 million miles per hour, but not aimlessly. Every spiral, every star, even our own cosmic neighborhood is being pulled toward something colossal lurking in the shadows. Astronomers call it the Great Attractor, a gravitational anomaly so powerful it defies explanation. Hidden behind the thick dust and stars of the Milky Way's galactic plane, an area nicknamed the Zone of Avoidance, this enigma remains frustratingly out of view, like a puppet master concealed behind a cosmic curtain. What could wield such immense pull? Early observations suggested a concentration of mass equivalent to tens of thousands of Milky Ways, possibly a supercluster of galaxies lurking in the darkness. But as technology pierced through the Zone of Avoidance, the mystery only deepened. The Norma cluster, a dense gathering of galaxies, was found near the epicenter, yet its gravity alone couldn't account for the violent tug we feel. Some theorists speculate about even larger structures, vast walls of galaxies stretching across hundreds of millions of light-years, their combined gravity bending the fabric of spacetime itself. Others whisper about exotic possibilities, cosmic strings, concentrations of dark matter we can't yet detect, or even flaws in our understanding of gravity on intergalactic scales. The hunt continues. Infrared and radio telescopes, like the groundbreaking work of the Parkes Observatory, have mapped strange filaments of galaxies all flowing toward this invisible behemoth. But with every answer, new questions arise. Is the Great Attractor itself being pulled by something even larger? Could it be a node in a sprawling cosmic web, part of a pattern we're only beginning to trace? One thing's certain: this isn't just a curiosity. It's a reminder that for all our maps of the universe, we're still navigating blindfolded, drawn toward mysteries we can't yet see. The universe is unimaginably vast, with billions of galaxies, each containing billions of stars. Statistically speaking, life should be everywhere. So why does the cosmos feel so silent? This is the Fermi Paradox, a question that's haunted scientists for decades. Named after physicist Enrico Fermi, who famously asked, "Where is everybody?" During a casual lunchtime conversation in 1950, the paradox exposes a glaring contradiction. Given the sheer number of habitable planets, advanced civilizations should have arisen long before us. We should see their ships, their megastructures, their radio signals flooding the void, and yet nothing. One chilling explanation is the Great Filter, a theoretical barrier that prevents life from progressing beyond a certain point. Maybe it's behind us, some improbable step like the emergence of DNA that makes our existence a cosmic fluke. Or worse, it's ahead of us: climate collapse, nuclear war, runaway AI. Any of these could be the bottleneck that silences civilizations before they ever reach the stars. Then there's the Berserker hypothesis. Malevolent machines or ancient aliens might be out there, systematically wiping out intelligent life before it becomes a threat. But not all theories are so grim. The zoo hypothesis suggests we're being deliberately ignored or quarantined, like animals in a galactic nature preserve. Others argue that advanced civilizations might communicate in ways we can't detect, using neutrinos or gravitational waves instead of crude radio signals. That's why projects like SETI and Breakthrough Listen scour the skies, not just for transmissions, but for anomalies, Dyson spheres swallowing starlight, or pulsed lasers flashing like cosmic lighthouses. And then there's the wow signal. In 1977, a radio telescope in Ohio caught a 37-second burst of noise so strong an astronomer scribbled, "Wow." In the margin, it came from the constellation Sagittarius, matched no known astronomical source, and has never repeated. Was it a glitch or a hello? The silence since then is deafening. Whether the answer is loneliness, doom, or something beyond our imagination, the Fermi Paradox forces us to confront a humbling truth. We might not just be searching for aliens. We might be searching for our own future. One moment the cosmos is silent, the next a blast of energy brighter than entire galaxies erupts. An explosion so intense it outshines 500 million suns, then vanishes in less time than it takes to blink. These are fast radio bursts, or FRB, some of the universe's most baffling and fleeting signals. First detected in 2007, these millisecond-long radio pulses race across billions of light-years, carrying more energy than our sun emits in 80 years. But where are they coming from, and why do some repeat like clockwork while others vanish without a trace? The first clue came in 2016, when astronomers caught an FRB repeating, proof that not all of them were cosmic one-hit wonders. Then, in 2020, a burst from our own galactic backyard cracked the case wide open. Tracing its origin to a highly magnetized neutron star called a magnetar, scientists finally had a smoking gun. These collapsed stellar cores, spinning at dizzying speeds with magnetic fields a trillion times stronger than Earth's, could whip up enough power to launch FRBs across the cosmos. But not all bursts fit this mold. Some arrive in predictable patterns, like FRB 121102, which fires off every 157 days like an interstellar metronome. Others erupt just once, leaving astronomers scrambling to explain their origins. Could collisions between neutron stars or evaporating black holes be responsible? Or more tantalizingly, could some FRBs be artificial? Enter CHIME, the Canadian Hydrogen Intensity Mapping Experiment, a telescope designed to catch these cosmic whispers in the act. Its array of half-cylinders scans the sky daily, uncovering dozens of new bursts and mapping their locations across distant galaxies. Meanwhile, projects like Breakthrough Listen analyze FRBs for signs of encoded patterns, just in case one turns out to be more than natural static. The most intriguing candidate, FRB 190520, a burst with a bizarre downward frequency drift, a fingerprint some argue resembles engineered signals. Of course, extraordinary claims require extraordinary evidence, and for now, natural explanations still lead the pack. Yet the deeper we dig, the stranger the mystery becomes. Some FRBs arrive with a twist. Their radio waves are so polarized, it's as if they've traveled through a cosmic funhouse mirror, warped by intense magnetic fields. Others seem to originate from galaxy clusters where new stars are barely forming, defying expectations. Every new detection peels back another layer, revealing a phenomenon far more complex than we first imagined. Whether natural or not, FRBs are more than cosmic curiosities. They're probes into the universe's most extreme environments, carrying secrets about the space between galaxies and the forces that shape it. And with every burst, they ask us the same thrilling question: what else are we missing? At the edge of the observable universe, where light has traveled for billions of years just to reach us, there are objects so luminous they defy comprehension. Quasars, short for quasi-stellar radio sources, are the cosmos's ultimate powerhouses, shining with the brilliance of a trillion suns packed into a region no larger than our solar system. These aren't just bright objects, they're time capsules, their light revealing the universe's wild teenage years, when chaos and creation collided on an unimaginable scale. And at their hearts lies the engine of their fury: supermassive black holes, voracious beasts feeding on gas, dust, and entire stars. How does a black hole, an object so dense not even light can escape, become the universe's brightest beacon? The answer lies in the maelstrom of matter swirling around it. As gas spirals inward at nearly the speed of light, friction heats it to millions of degrees, creating a swirling disk of plasma that glows brighter than all the stars in a galaxy combined. Magnetic fields twist this chaos into jets, twin beams of energy shooting out for thousands of light years, punching through intergalactic space like cosmic blowtorches. Hubble's images capture these jets in stunning detail, their eerie glow stretching across the void like celestial searchlights. But quasars aren't just spectacular, they're crucial architects of the cosmos. In the early universe, their intense radiation ionized the fog of hydrogen that filled space, carving out the transparent universe we see today. Their outflows seeded galaxies with heavy elements, and their gravity may have dictated where galaxies clustered. Yet for all their brilliance, quasars are fleeting. As their black holes devour the last scraps of nearby matter, the lights dim. Some shut off entirely, leaving behind dormant giants like the one lurking in our own Milky Way. Others flicker back to life when a passing star or gas cloud reignites the feast. The mystery deepens when we spot quasars that shouldn't exist. Take J0313-4342. A quasar so massive and so ancient it challenges our understanding of how black holes grow. Formed just 670 million years after the Big Bang, its black hole weighs in at over 1 billion solar masses, a size theorists struggle to explain without invoking exotic physics or freakish early conditions. Then there's the case of quasars embedded in seemingly empty space, their host galaxies mysteriously absent. Are they orphans ejected during galactic collisions, or evidence of an even stranger phenomenon? Every quasar tells a story, but we're only beginning to decipher their language. With tools like the James Webb Space Telescope peering even farther back in time, we're uncovering quasars in ever more improbable settings, rewriting the timeline of cosmic evolution. One thing's clear, these ancient monsters didn't just light up the universe, they shaped it, and in their fading glow, we're finding clues to our own origins, written in the fire of the first dawn. Stretching across the sky like a cosmic bruise, the cold spot is one of the universe's most unsettling anomalies. Found in the constellation Eridanus, this patch of the cosmic microwave background, the faint afterglow of the Big Bang is significantly colder than its surroundings, as if a chunk of the early universe simply forgot to warm up. First spotted by NASA's Wilkinson Microwave Anisotropy probe in 2004, and later confirmed by the Planck satellite with razor-sharp precision, this region defies easy explanation. It's not just a statistical fluke. The odds of such a cold area appearing randomly are about 1 in 50. So what's casting this cosmic shadow? One leading theory points to a supervoid, an enormous, nearly empty region of space where matter is strangely sparse. Light passing through such a void would lose energy, a phenomenon known as the integrated Sachs-Wolf effect, potentially explaining the temperature dip. But here's the catch. Surveys like those from the Anglo-Australian telescope found no void large enough to account for the cold spot's chilling intensity. The mystery deepened when some researchers claimed to find a sparse region, but its size and emptiness still fell short of what the physics demanded. Then there's the far wilder idea the cold spot might be a bruise from a collision with another universe. In the multiverse theory, bubble universes could bump against each other during cosmic inflation, leaving imprints in the CMB. The cold spot's unusual polarization patterns and sharp edges have fueled speculation that we're seeing the fingerprint of a parallel cosmos nudging our own. Critics counter that such a claim leans too heavily on unproven physics, and Occam's razor favors more mundane explanations. Yet the Planck data's lingering anomalies keep the door ajar for extraordinary possibilities. Planck's stunning visualizations reveal the cold spot in exquisite detail, its blue hues standing out against the warmer oranges and reds of the surrounding CMB. These maps aren't just snapshots, they're forensic tools. By analyzing the spot's size, shape, and polarization, scientists hunt for clues. Could it be a rare statistical outlier in an otherwise uniform cosmos, a flaw in our understanding of inflation, or something beyond our current models entirely? The cold spot's enigma forces us to confront how much we still don't know about the universe's infancy. Whether it's a cosmic ghost, a window into the multiverse, or just an artifact of incomplete data, one thing's certain: it's a reminder that even our most precise maps of the cosmos are still dotted with terra incognita. And in those blank spaces, the most thrilling discoveries await. The universe threw us a curveball in October 2017, a fast-moving, faint speck of light streaking through our solar system unlike anything we'd seen before. Telescopes swiveled to catch a glimpse, but by the time astronomers realized what they were looking at, it was already speeding away. This wasn't just another asteroid or comet. It was our first confirmed interstellar visitor, a messenger from the void between stars. They named it Oumuamua, Hawaiian for scout or messenger. But what it carried wasn't a greeting, it was a riddle wrapped in cosmic mystery. First, there was its shape. Most asteroids and comets are lumpy, potato-like blobs. Oumuamua, a needle. Estimates suggested it was up to 10 times longer than it was wide, tumbling end over end like a discarded cigarette. Then came the real shocker: its speed. As it hurtled away from the sun, it accelerated in a way gravity alone couldn't explain. Comets usually get a speed boost from vaporizing ice, creating a visible coma, a hazy cloud of gas and dust. But Oumuamua left no such trail. It was dry, silent, and utterly perplexing. Cue the theories. Harvard astrophysicist Avi Loeb made headlines suggesting Oumuamua might be artificial. Perhaps a fragment of alien technology, like a broken light sail drifting between the stars. The idea wasn't entirely far-fetched. Human projects like Breakthrough Starshot aim to send tiny light sails to nearby stars propelled by lasers. Could Oumuamua be evidence someone or something had already perfected the technique? Others countered with natural explanations. A hydrogen iceberg, for instance, might have accelerated silently as the sun's heat stripped away its outer layers, leaving no dusty trail. Or maybe it was a shard of a Pluto-like world, sheared off by some ancient collision and sent careening into the void. Then, in 2019, a second visitor arrived: Comet Borisov. Unlike Oumuamua, Borisov was textbook, a fuzzy coma, a classic tale, moving exactly as a comet should. The contrast was striking. One visitor obeyed the rules, the other rewrote them. To this day, Oumuamua defies categorization. Was it a cosmic oddity, a herald of unseen phenomena, or something even more extraordinary? With no more data to collect, it remains a fleeting enigma, an invitation to wonder what else might be sailing through the dark just beyond our reach. The James Webb Space Telescope and upcoming observatories like the Vera Rubin Telescope are poised to spot more of these interstellar strangers. Each one could be a key to unlocking secrets of distant star systems, or a reminder that the universe still holds surprises no model predicted. Oumuamua didn't just pass through our solar system. It left us with a question echoing across the light years. What else is out there? Some stars flicker like candles in the wind, but KIC 8462852, better known as Tabby's star, doesn't just flicker. It plummets. Nestled in the constellation Cygnus, this otherwise ordinary F-type star first grabbed astronomers' attention in 2015 when data from the Kepler Space Telescope revealed something bizarre. Over several years, its light dimmed by up to 22% in irregular, jagged dips, as if something colossal was passing in front of it, not the clean, periodic dimming of an orbiting planet. This was chaos, a celestial light switch being flipped at random. Initial theories pointed to a swarm of comets, thousands of them, trailing enough dust to blot out a fifth of the star's glow. But comets couldn't explain the star's long-term fading. documented by century-old photographic plates showing it had dimmed by nearly 15% since the 1890s. Then came the piece de resistance, a paper by astronomer Jason Wright, who floated an idea straight out of sci-fi. What if we were seeing a partially built Dyson sphere, a megastructure designed by an advanced civilization to harness its star's energy? The internet erupted. Suddenly, Tabby's star wasn't just an anomaly. It was a beacon. Enter the citizen scientists, the crowdsourced Planet Hunters project, where volunteers sifted through Kepler data for unusual patterns, had actually flagged the star years earlier. Amateurs became crucial, tracking the star's erratic behavior with backyard telescopes. Their observations revealed something even stranger. The dimming wasn't symmetrical. Some wavelengths of light were blocked more than others, suggesting whatever obscured the star wasn't solid. Not a monolithic megastructure then, but what? The James Webb Space Telescope finally cracked the case in 2023. Its infrared eyes detected a telltale excess of heat signature of fine dust particles, likely from pulverized asteroids or evaporating comets. No Dyson spheres, no alien engineering, just a messy, turbulent system, possibly still reeling from a catastrophic collision. Yet Tabby's star's legacy endures. It taught us how unpredictable the cosmos can be and how much we still rely on curiosity, whether from professionals or amateurs staring at screens in their living rooms. Most of all, it's a reminder that the universe doesn't need aliens to surprise us. Sometimes the truth is weirder than fiction. Imagine a cosmic vault so secure that once something crosses its threshold, it's locked away forever. No returns, no records, no traces. That's how black holes were supposed to work, but Stephen Hawking shattered that illusion in 1974 when he unveiled a bombshell. Black holes aren't eternal. They leak. Through a bizarre quantum quirk, they emit faint radiation, now called Hawking radiation, slowly evaporating over eons until they vanish entirely. And that's where the paradox begins. According to quantum mechanics, information, the fundamental blueprint of every particle that ever fell into the black hole, can never be destroyed. Yet if the black hole disappears, where does that information go? This isn't just a philosophical puzzle. It's a crisis at the heart of physics, forcing us to choose between two pillars of science: general relativity or quantum theory. Something has to give. Hawking's math suggested the information was truly lost, erased from existence as the black hole evaporated. The implications were staggering. If correct, it would mean the universe forgets reality itself has an undo button. Quantum mechanics, which insists information is always preserved even if scrambled beyond recognition, would collapse like a house of cards. The scientific community split. Some, like Hawking himself, initially embraced information loss as a radical new truth. Others, like Leonard Susskind, revolted, sparking a decades-long battle dubbed the Black Hole War. Susskind argued that if quantum mechanics was wrong about something this fundamental, our entire understanding of particles, forces, and even time might need to be rewritten. Enter the firewall paradox, a terrifying twist in the saga. In 2012, a quartet of physicists proposed that if information must escape a black hole, it could only do so by creating a searing wall of energy at the event horizon. Not the gentle fade-out predicted by relativity, but a violent inferno that would incinerate anything crossing it. This wasn't just science fiction. It was a direct challenge to Einstein's vision of an astronaut smoothly falling into oblivion. Firewalls implied black holes were cosmic killers twice over, first with their gravity, then with their flames. The backlash was immediate. If firewalls existed, they'd violate the equivalence principle, a cornerstone of general relativity. Yet without them, how could information ever escape? The solution might lie in rewiring how we see reality itself. The holographic principle, born from string theory, suggests a wild possibility. Everything inside a black hole might be encoded on its two-dimensional surface like a cosmic DVD. Information isn't destroyed, it's smeared across the event horizon in a quantum blur, eventually escaping as Hawking radiation. It's as if the universe compresses 3D experiences into a 2D snapshot, preserving the data in a form we're only beginning to decode. Recent breakthroughs in calculating entropy, a measure of information in Hawking radiation, lend weight to this idea, hinting that black holes might scramble information rather than erase it, like a celestial shredder that leaves the documents intact, just cut into confetti. Yet mysteries remain. If information escapes, how? Through subtle correlations in the radiation, via hidden quantum tunnels, or some mechanism we haven't yet imagined. Experiments are impossible. No lab can recreate a black hole's extremes. But theorists press on, weaving intricate models where spacetime itself is a tapestry of entangled quantum bits. The stakes couldn't be higher. Solving the paradox might unlock a unified theory of quantum gravity, revealing how the universe stitches together the very large and the very small. One thing's certain, black holes aren't just cosmic trash compactors. They're mirrors, forcing us to confront the frayed edges of our understanding. Every proposed solution peels back another layer, exposing deeper questions about the nature of reality. And in that tension between what we know and what we must know lies the thrill of the hunt. Somewhere in the cosmos, there's a hole, not just a gap between galaxies, but a yawning chasm so vast it could swallow thousands of Milky Ways without a trace. The Boötes Void, nicknamed the Great Nothing, sprawls across 330 million light-years of near-total emptiness. To put that in perspective, if you dropped Earth at its center, our most powerful telescopes wouldn't see a single galaxy until their gaze reached the void's edges. This isn't just empty space, it's a desert on a scale that defies logic, and the Boötes Void isn't alone. The universe is pockmarked with these abysses, each one a challenge to everything we thought we knew about how galaxies form. Normally, galaxies cluster like cities along invisible highways of dark matter, drawn together by gravity. But voids flip that script. Inside them, matter is so sparse that galaxies are stranded, isolated islands adrift in nothingness. The few that do exist here, known as void galaxies, evolve in eerie solitude. Without the constant collisions and mergers that shape their crowded cousins, these loners age differently. They're often smaller, bluer, and strangely pristine, their gas reservoirs untouched by the violence of galactic downtowns. Hubble's snapshots reveal them as cosmic fossils frozen in time. Yet the real mystery isn't what's inside these voids, it's how they formed at all. Simulations suggest they should be filled with faint, dwarf galaxies, the leftover scraps of cosmic evolution. Instead, the Boötes Void holds just 60 galaxies where thousands should float. One theory points to void swelling, where dark energy stretches these regions faster than galaxies can form, diluting matter like ink in an expanding pool. Others propose that voids are the inverse of galaxy clusters, not accidents, but fundamental features of the universe's sponge-like structure, woven into existence during the Big Bang's first seconds. The most unsettling possibility, voids might be growing. As dark energy accelerates the universe's expansion, these empty regions could stretch until entire galaxy clusters are ripped apart, their stars left drifting in eternal night. It's a future where the cosmos doesn't just fade, it unravels. For astronomers, voids are more than curiosities. They're laboratories. By studying how light bends around their edges or how galaxies behave in isolation, we're deciphering the hidden rules of cosmic architecture. Projects like the Dark Energy Survey map these voids in 3D, revealing how they warp the paths of supernovas and distort the cosmic microwave background. Each observation peels back another layer, exposing how emptiness shapes the universe as surely as matter does. The Boötes Void and its kin remind us that the universe isn't just about what glows, it's about what doesn't. In those silent expanses, we're finding clues to the fate of everything, written in the negative space of the cosmos. The cosmic microwave background, the oldest light in the universe, should be a random, scrambled snapshot of the infant cosmos, a patchwork of hot and cold spots with no underlying order. But when scientists mapped it with unprecedented precision, they found something that sent chills down their spines, a pattern. Not just any pattern, but an eerie alignment with our own solar system's plane, as if the universe itself had drawn a target around us. They called it the axis of evil, a tongue-in-cheek name masking a profound unease. This wasn't supposed to happen. The cosmos doesn't play favorites, yet here we are, staring at a cosmic fingerprint that seems to point directly at Earth. The discovery emerged from data collected by NAS, a Wilkinson microwave anisotropy probe, and later the Planck satellite. These missions mapped the CMB's temperature fluctuations, tiny variations representing the seeds of galaxies. According to the standard cosmological model, these fluctuations should be isotropic, meaning no direction in space should stand out. But the data revealed a startling correlation. The largest scale hot and cold spots aligned along an axis that improbably matched the ecliptic, the plane of Earth's orbit around the Sun. The odds of this happening by chance, less than 1 in 1,000. Either we're witnessing a statistical fluke of cosmic proportions, or something fundamental in our understanding of the universe is missing. Skeptics argue it's an illusion, a trick of observation. Perhaps our instruments, calibrated within the solar system, picked up contamination from interplanetary dust or the solar wind. Others point to foreground emissions from the Milky Way, a celestial smokescreen distorting the CMB's true signal. But after years of painstaking analysis, the anomaly persists. Planck's team even tried rotating their maps, testing hundreds of theoretical models. The axis stubbornly remained, like a shadow no amount of light could dispel. Then come the radical explanations. Could it be evidence of a pre-Big Bang structure, a relic of some primordial asymmetry imprinted on space-time itself? Or does it hint at a universe far stranger than we've imagined, one where the laws of physics vary depending on direction, a concept called anisotropic cosmology? The most unsettling possibility, that we're seeing the tug of a neighboring universe, its gravity subtly warping ours like a finger pressed against the fabric of reality. The implications are staggering. If the axis is real, it undermines the cosmological principle, the cornerstone assumption that the universe is uniform in all directions. Without this principle, our entire understanding of cosmic expansion, dark energy, even the Big Bang might need rethinking. Yet despite the tension, the axis of evil isn't a crisis, it's an invitation. A clue that the universe still holds cards it hasn't revealed. And as new telescopes probe deeper into the CMB's whispers, we're left with a haunting question. Are we staring at a flaw in our maps or a crack in the foundations of reality itself? When a star goes supernova, the explosion is so violent it should annihilate everything in its vicinity: planets, asteroids, even its own stellar companions. Yet in 1992, astronomers made an impossible discovery, a trio of worlds orbiting the charred corpse of a dead star. The pulsar PSRB 1257+12, spinning furiously at over 6,000 revolutions per minute, shouldn't have had a single pebble left in its orbit after the cataclysm that birthed it. And yet there they were, 3 planets dancing around a cosmic zombie. Welcome to the enigma of pulsar planets, where the rules of survival were written in fire and rewritten by chaos. These aren't just any dead stars. Pulsars are neutron stars, the dense cores left behind after a supernova, so compressed that a teaspoon of their material weighs 1 billion tons. They're laced with magnetic fields strong enough to rip atoms apart and spew jets of radiation like a lighthouse from hell. Any planets orbiting them endure hurricane-force particle winds and lethal doses of X-rays. Conventional wisdom said planets couldn't form here. The primordial disks of gas and dust that birth worlds around young stars would have been vaporized in the supernova's blast. So how did these defiant worlds come to be? One theory suggests they're cosmic phoenixes, second-generation planets forged from the ashes. When a massive star explodes, not all its material escapes. Some falls back, forming a debris disk around the newborn pulsar. Out of this graveyard, new planets could coalesce, sculpted by the pulsar's relentless radiation. Another, darker possibility involves stellar cannibalism. If the pulsar had a companion star before the explosion, the supernova's shockwave might have shredded it, leaving behind a ring of stolen matter that later clumped into planets. Observations of PSRB 1257 plus 12's planets support this. Their orbits are bizarrely precise, as if arranged by some violent reordering. But the strangest twist came in 2006, when astronomers found a pulsar with a planet that shouldn't exist even by these extreme standards. PSR J1719-1438's world is a gas giant, 10 times heavier than Jupiter, orbiting its dead star every 2 hours. At that distance, the pulsar's radiation should have blown the planet apart like tissue paper in a hurricane. Unless, and here's the kicker, it wasn't always a gas giant. Some researchers speculated began as a white dwarf, a dead star in its own right, only to have the pulsar strip away its outer layers over eons, leaving behind a naked core masquerading as a planet. Pulsar planets don't just defy expectations, they rewrite the playbook. Their existence hints at a universe far more inventive than we imagined, where death gives birth to new worlds under conditions that would vaporize anything in our solar system. And they raise a tantalizing question. If planets can thrive in these graveyards, where else might we find life clinging to the edge of oblivion? These aren't just survivors. They're monuments to chaos, proof that even in the universe's most hostile corners, the improbable becomes inevitable. Two of the universe's most trusted measuring tapes are giving us wildly different answers, and cosmologists are scrambling to explain why. On one side, we have the cosmic microwave background, the afterglow of the Big Bang captured by missions like Planck, telling us the universe is expanding at 67 kilometers per second per megaparsec. On the other, nearby Cepheid variables, pulsating stars used as cosmic yardsticks, insist the number is 73. A mere 6 might not sound like much, but in the high-stakes world of precision cosmology, it's a 5 sigma discrepancy. That's like 2 GPS devices giving directions to the same address, only to realize one is leading you to a different continent. Welcome to the Hubble tension, a crisis that's forcing us to question whether we've misunderstood the cosmos itself. Let's break it down. Cepheids are the gold standard for local measurements. These stars pulse with a rhythm directly tied to their brightness, allowing astronomers to calculate distances with razor-sharp accuracy. By observing them in galaxies relatively close to ours, teams using the Hubble Space Telescope have painstakingly built a cosmic distance ladder, rung by rung, to measure the universe's expansion rate. Their answer, 73, but when we look at the CMB, the faint echo of the universe's infancy, Planck's data, combined with our understanding of dark matter and dark energy, points squarely to 67. The gap persists even after accounting for every known source of error. Either someone's math is catastrophically wrong, or the universe played a trick on us. The implications are staggering. If both measurements are correct, it suggests something fundamental is missing from our cosmic playbook. One leading fix is early dark energy, a hypothetical burst of repulsive force that briefly flared up in the universe's first 100,000 years, altering the CMB's signature without leaving traces elsewhere. Think of it as a cosmic speed boost in the early sprint, fading before the marathon of expansion we see today. Another proposal tinkers with gravity itself, suggesting Einstein's equations might need tweaking on cosmological scales. Modified gravity theories like modified Newtonian dynamics have long lurked at physics fringes, but the Hubble tension is giving them fresh urgency. Then there's the nuclear option. What if our entire framework for interpreting the CMB is flawed? The Planck measurements assume the universe is flat, homogeneous, and dominated by dark energy, a model called lambda-cidium that's been cosmology's backbone for decades. But if any of those assumptions are off, say, if dark energy evolves over time or the universe isn't as uniform as we thought, the CMB's expansion rate could shift dramatically. It's like realizing the ruler you've been using all along was printed on stretchy fabric. The stakes couldn't be higher. Resolving the tension might require rewriting textbooks or uncovering entirely new physics. Upcoming telescopes like the Roman Space Telescope and the Vera Rubin Observatory are poised to deliver even sharper measurements, but for now the gap remains. And in that gap, something extraordinary lurks, the possibility that our universe, for all our maps and models, still holds secrets we haven't even thought to question. The Hubble tension isn't just a numbers game. It's a cosmic wake-up call, reminding us that even the most trusted landmarks in science are only as solid as the next revelation. Most black holes anchor galaxies, lurking at the center like cosmic sentinels, but not all play by those rules. Some go rogue, drifting through the void like silent predators. These aren't just theoretical specters. Astronomers have caught them in the act using a trick called microlensing. When one of these invisible monsters passes between us and a distant star, its gravity bends the starlight like a lens, briefly magnifying it. That flicker in the night, that's a black hole's shadow, a ghostly signature revealing its presence. The numbers are staggering. Estimates suggest there could be millions wandering our galaxy alone, untethered from any star or system. And some of them are shockingly close. How does a black hole go rogue? The answer lies in cosmic violence. When galaxies collide, their central supermassive black holes spiral toward each other, locked in a gravitational dance. As they merge, the resulting kick can be so powerful it flings the newborn black hole clean out of its galaxy. Other rogues might be born from the collapse of failed supernovas, massive stars that imploded without the fanfare of an explosion, leaving no trace but a dark, hungry remnant. The real question is, what happens if one crosses our path? A rogue black hole wouldn't announce itself with swirling accretion disks or blazing jets. It would slip through the solar system like a thief, its gravity the only warning. Planets could be flung into deep space, their orbits shredded in an instant. The sun itself might start wobbling, pulled by an invisible force we couldn't see until it was too late. But here's the twist: these drifters might also be lifesavers. Some theories suggest rogue black holes could serve as anchors for future civilizations, their immense gravity harnessed for slingshot maneuvers across the galaxy. Others speculate they could be wrapped in dark matter halos, acting as invisible lighthouses for mapping the universe's hidden structure. For now, hunting them remains a game of patience and precision. Projects like the upcoming Nancy Grace Roman Space Telescope aim to spot hundreds more through microlensing, piecing together their paths like interstellar forensics. Each discovery peels back another layer of their mystery: how many are out there, where they're headed, and whether we should fear their approach or marvel at their solitude. One thing's certain: the universe has a way of reminding us that even the darkest corners are full of surprises. The Milky Way seems like a peaceful island of stars, but hidden in its spiral arms and halo are scars from a violent past. Our galaxy is a cannibal, and the bones of its victims are strewn across the cosmos. Take Gaia Enceladus, a dwarf galaxy that once drifted too close. Roughly 10 billion years ago, this celestial trespasser, about a quarter the Milky Way size, was ripped apart by our galaxy's gravity, its stars scattered like cosmic confetti. Today, its remnants linger in the galactic halo, a ghostly fingerprint detectable only by their unusual orbits and chemical signatures. Thanks to the Gaia spacecraft's precision mapping, we've traced these rogue stars back to their doomed progenitor, piecing together the aftermath of a collision that reshaped our galaxy's infancy. Then there's the Sagittarius dwarf, a smaller but equally tragic tale. This pint-sized galaxy has been circling the Milky Way for billions of years, and with each pass, our galaxy steals more of its stars, stretching them into glittering streams that wrap around us like celestial spaghetti. The southern hemisphere's night sky holds the evidence the Sagittarius Stream, a river of stars torn from their home, now orbiting silently in the Milky Way's grasp. Telescopes like the Dark Energy Survey have mapped these tendrils in exquisite detail, revealing how gravity's tug of war warps entire galaxies into debris. But the most dramatic feast is yet to come. In about 4.5 billion years, the Milky Way will collide with its largest neighbor, Andromeda. Simulations predict a slow-motion dance of destruction. First, the galaxies will stretch each other's stars into tidal tails, then merge into a single, bloated elliptical galaxy nicknamed Milkdromeda. The Sun will likely survive, but its familiar constellations will be obliterated, replaced by a chaotic sky streaked with new starlight. Hubble's observations of other merging galaxies, like the antennae galaxies, show us glimpses of this future spirals twisted into ruin, star-forming regions ignited by the chaos. Yet for all the violence, galactic cannibalism is also a creative force. Each collision seeds the Milky Way with fresh stars, heavy elements, and even the building blocks for new planets. Some astronomers speculate that our own solar system's existence might trace back to one of these ancient mergers, that the gold in your jewelry or the uranium in reactors was forged in the heart of a dwarf galaxy, later stolen by the Milky Way's gravity. What's clear is that the universe runs on cycles of destruction and rebirth. Far from being an isolated oasis, the Milky Way is a product of countless collisions, each one leaving its mark on the stars we see tonight. And as we look toward Andromeda's looming approach, we're not just observers of this process, we're future participants in the greatest cosmic feast of all. Consider a star so dense that a single teaspoon of its material would weigh 1 billion tons. Now imagine that star cracking open like an egg. These are neutron starquakes, cosmic tremors that unleash more energy in a millisecond than our Sun emits in 100,000 years. Born from the collapse of massive stars, neutron stars are nature's most extreme physics labs, packing more mass than the Sun into a sphere barely the size of a city. Their crusts, a crystalline lattice of iron nuclei squeezed into a rigid shell, are under unimaginable strain. And when that strain becomes too much, the star's surface shatters in violent starquakes, sending shockwaves rippling through spacetime itself. The aftermath is spectacular. In 2004, astronomers witnessed a magnetar, a neutron star with a magnetic field 1,000 trillion times stronger than Earth's, unleash a flare so bright it briefly outshone the entire Milky Way. This wasn't a supernova, it was the seismic aftermath of a crustal rupture, a fracture that released pent-up magnetic energy in a single, blinding flash. For 1/10 of a second, the explosion flooded gamma-ray detectors across the solar system, ionizing Earth's upper atmosphere from 50,000 light-years away. Had it happened within 10 light-years, it could have stripped our ozone layer, triggering mass extinctions. But starquakes aren't just celestial light shows, they're cosmic messengers. When LIGO detected gravitational waves in 2017, the ripples came from colliding black holes, yet neutron starquakes, though smaller in scale, also warp spacetime. Tiny tremors, called glitches, momentarily speed up a neutron star's rotation as its rigid crust adjusts like a skater pulling in their arms. Some theorists suggest these mini-quakes could produce faint gravitational waves, whispering secrets about the star's internal structure. Imagine listening to the vibrations of a bell to deduce its shape, except this bell is 20 kilometers wide and rings at frequencies beyond human comprehension. The most bizarre twist, neutron star crusts might be stranger than diamond. Simulations suggest their interiors could form nuclear pasta, layers of protons and neutrons twisted into shapes resembling spaghetti or lasagna sheets by the crushing gravity. A quake here wouldn't just break rock, It might snap these quantum noodles, releasing bursts of neutrinos or even triggering magnetic reconnections that light up the surrounding nebula. Every detected starquake is a Rosetta Stone, decoding the physics of matter under conditions no lab could recreate. From the hyper-dense crusts to the superfluid cores, these events peel back layers of mystery, revealing a universe where even the dead stars refuse to stay quiet. And with every crack in the cosmos, we're reminded, the most violent upheavals often hold the keys to understanding the fabric of reality itself. It was a quiet night in Ohio on August 15, 1977, when a radio telescope at the Big Ear Observatory caught something that would haunt astronomers for decades. A 72-second burst of noise so peculiar that the scientist who spotted it circled the printout and scribbled 3 letters in red ink. Wow. The signal, blasting in at 1420 MHz, a frequency notably silent under natural cosmic conditions, matched almost exactly what theorists predicted an alien transmission might sound like. Narrowband, strong and utterly unexplained, for that brief moment it seemed humanity might have just overheard its first cosmic hello, then nothing. No repeat, no pattern, just silence stretching across 46 years and counting. What made the wow signal so electrifying wasn't just its intensity, 30 times louder than the background noise, but its shape. It flared and faded like a siren passing by, a signature consistent with something crossing the telescope's field of view, earthly interference unlikely. The frequency fell within the protected waterhole, a band reserved for astronomical research free of human transmissions, a satellite none were known to broadcast at that exact wavelength. Even meteors burning up in the atmosphere, a common source of radio spikes, couldn't explain such a focused, narrowband signal. Then came the comet theory. In 2016, an astronomer proposed that 2 passing comets, their hydrogen clouds evaporating in sunlight, might have mimicked an artificial transmission. But the math crumbled under scrutiny. The comets weren't in the right part of the sky when the signal arrived, and their hydrogen emissions would have been far too diffuse to match WOW's razor-sharp profile. The clincher, Big Ear, had 2 feed horns scanning the sky simultaneously. If the signal were celestial, both should have caught it seconds apart. Only one did, deepening the enigma. Theories veered into the extraordinary. Could it have been an alien beacon sweeping past Earth like a lighthouse beam? Or perhaps a military experiment, declassified decades later but still unacknowledged? The most haunting possibility, it was intentional, a deliberate broadcast that ended abruptly, either because its senders moved on or because we failed to reply in time. SETI's subsequent efforts, scanning the same patch of Sagittarius thousands of times, have found only silence. Even today, upgraded arrays like the Allen Telescope cluster monitor the region, listening for an echo of that mysterious burst. Yet the WOW signal's legacy isn't just about what we didn't hear. It's about how fragile first contact might be, a single blip in the void, easily missed or dismissed. In a universe where civilizations could rise and fall between the stars, 72 seconds might be all we get. The signal didn't just vanish. It left us with a question written across the cosmos: were we meant to hear it? And if so, why hasn't anyone called back? Far beyond Neptune, in the frozen fringes of our solar system, something massive is tugging at the cosmos. The evidence comes not from what we see, but from what moves, a cluster of icy bodies in the Kuiper belt behaving as if an invisible hand is herding them. These objects, like the dwarf planet Sedna, follow bizarre, elongated orbits all tilted in the same direction, a pattern so unlikely to occur naturally that astronomers have spent years chasing one explanation: a hidden giant lurking in the dark. They call it Planet 9, a world up to 10 times heavier than Earth, orbiting so far from the Sun that a single year there could last 20,000 of our own. The clues first surfaced in 2014, when astronomers Chad Trujillo and Scott Shepard noticed a strange alignment in the orbits of distant Kuiper belt objects. Their paths weren't randomly scattered like scattered marbles, they pointed eerily in the same general direction. Then, in 2016, Caltech's Konstantin Batygin and Mike Brown ran the numbers, showing the odds of this clustering happening by chance were a mere 0.0002%. The only plausible culprit, a distant, undiscovered planet, its gravity sculpting these frozen worlds like a hidden puppeteer. But Planet 9 isn't the first phantom world to haunt astronomers' calculations. Decades earlier, similar anomalies led to the hunt for Titch, a hypothetical gas giant proposed to explain peculiar comet orbits in the Oort cloud. Unlike Planet 9, Titch was ruled out when NASA, a wise telescope, scanned the skies and found no trace of it. Yet Planet 9's case is different. Its predicted orbit, while vast, places it closer and dimmer, a cold, shadowy realm where even our best telescopes struggle to see. The search is heating up. The upcoming Vera Rubin Observatory, with its 3 billion pixel camera, will scan the southern sky every few nights, spotting movement too subtle for current telescopes to catch. If Planet 9 exists, its slow crawl against the stars could finally betray its presence. Some theorists suggest another approach, watching for its gravitational fingerprint on spacecraft like Cassini, whose orbit might wobble imperceptibly if tugged by something unseen. The implications are staggering. Planet 9 could rewrite solar system history, possibly stolen from another star in our sun's infancy. Its discovery wouldn't just add another world to our maps, it would reveal how dynamic and chaotic our cosmic neighborhood truly is. For now, it remains a shadow in the equations, a gravitational whisper teasing us with the possibility that even in our own backyard, the universe still has secrets to spill. At the smallest scales imaginable, far smaller than an atom, even tinier than a quark, spacetime itself may churn like a stormy sea. This is quantum foam, a frothing turbulence in the very fabric of reality where particles wink in and out of existence so fast they barely register as a flicker. Picture the surface of a boiling ocean, but instead of water, it's space and time bubbling with energy, constantly twisting and reforming. At these scales, the smooth, curved geometry of Einstein's spacetime shatters into something wild and unpredictable, governed by the chaotic rules of quantum mechanics rather than the orderly equations of relativity. The foam isn't empty. Empty space, as it turns out, is anything but. Even in a perfect vacuum, energy seethes under the surface, particle-antiparticle pairs popping into existence, borrowing energy from the void before vanishing again. This is vacuum energy, the same force behind dark energy's cosmic push, and it's the fuel for the foam's eternal churn. Quantum mechanics allows these fleeting particles to exist because they're too short-lived to violate the laws of conservation, like a cosmic game of buy now, pay later, where the debt is always settled before the ledger is checked. In this turbulent foam, wormholes, hypothetical tunnels through space-time, might form naturally, bridging distant points in the universe before collapsing faster than light can traverse them. Some theories suggest these microscopic shortcuts could be stabilized, stretched, and even traversed with enough exotic matter or negative energy. But here's the catch: the energy required to hold one open might exceed anything the universe can provide, turning interstellar shortcuts into a physicist's pipe dream. The real conflict arises when we try to merge this chaotic quantum world with the smooth, deterministic fabric of general relativity. Einstein's equations describe gravity as the curvature of spacetime, a majestic, unbroken landscape. But at Planck scales, where quantum foam reigns, spacetime becomes a frenzied mess of fluctuations, leaving no clear way to stitch the two theories together. This is the heart of the unification problem, the reason theories like string theory and loop quantum gravity were born, to reconcile the frenzy of the very small with the serenity of the very large. Experiments to probe quantum foam directly are, for now, beyond our reach. The Planck length, a scale so small that a single proton is like a galaxy in comparison, is unimaginably tiny. But indirect hints might lie in high-energy particle collisions or subtle distortions in distant starlight. Some theorists even suggest that if spacetime is foamy, it could blur the images of faraway gamma-ray bursts like looking through a frosted window. Quantum foam isn't just a curiosity, it's a frontier, a place where the laws of physics as we know them break down, where reality itself becomes a statistical probability rather than a fixed certainty. And in its chaos, we might just find the key to unlocking the universe's deepest secrets, if only we can learn to read the froth. If black holes are the universe's ultimate vacuum cleaners, sucking in everything that crosses their path, then white holes are their cosmic opposites, theoretical fire hoses blasting matter and energy outward with no way back in. Imagine a black hole running in reverse. Instead of an event horizon trapping light forever, a white hole would have an anti-event horizon, a boundary where nothing can enter, only escape. The equations of general relativity allow for such bizarre objects, painting them as the other side of the black hole's tunnel, spewing out everything the black hole devoured. But here's the catch: while black holes are confirmed by countless observations, white holes remain stubbornly hypothetical, their existence lingering in the realm of mathematical possibility rather than physical proof. So why haven't we spotted one? For starters, white holes violate the second law of thermodynamics, which dictates that entropy, the universe's measure of disorder, must always increase. A white hole spontaneously ejecting ordered energy into the cosmos would essentially be reversing the arrow of time, creating a pocket of decreasing entropy in a universe that only moves toward chaos. Even stranger, general relativity suggests white holes could only form under conditions that defy causality, a universe with no past or one where time itself flows backward. If they do exist, they might be incredibly short-lived, exploding into existence and vanishing before our telescopes could catch them in the act. Yet the idea isn't entirely science fiction. Loop quantum gravity, a leading contender for unifying quantum mechanics and general relativity, offers a tantalizing twist. In this framework, a collapsing black hole might rebound at the quantum level, transforming into a white hole in a process called quantum bounce. Instead of ending as a singularity, a point of infinite density, the dying black hole would rebound, ejecting its contents back into the universe over billions of years. Some theorists even suggest primordial black holes from the early universe could have already undergone this transition, their white hole remnants lingering today as faint, high-energy bursts in the cosmic background. The most intriguing possibility, gamma-ray bursts, the most energetic explosions in the universe, could be white holes in disguise. These fleeting flashes of radiation, some lasting mere seconds, match the theoretical profile of a white hole's final eruption, a last gasp of energy before it winks out of existence. But without a smoking gun, like a burst with the exact spectral signature predicted by loop quantum gravity, the idea remains speculative. White holes challenge not just our understanding of physics, but our intuition about how the universe should behave. They're a reminder that the cosmos might still hold phenomena so strange, so counter to our experience, that they lurk just beyond the edge of observation. And if we ever do find one, it wouldn't just rewrite textbooks, it would force us to rethink the very nature of time, entropy, and the fate of everything swallowed by a black hole. For now, they remain cosmic phantoms, equal parts prediction and paradox, waiting in the equations for someone to prove they're more than just a beautiful idea. The universe is expanding, galaxies drifting apart except for one baffling exception. Hundreds of galaxy clusters are streaming in the same direction at breakneck speeds, as if pulled by an invisible hand from beyond the edge of everything we can see. Astronomers call this phenomenon dark flow, a cosmic current moving at nearly 2 million miles per hour toward something or somewhere we can't observe. The implications are staggering. Either we've stumbled upon the largest statistical anomaly in cosmology, or our universe is being tugged by a structure so colossal it lies outside our visible horizon. This discovery traces back to 2008, when a team analyzing X-ray emissions from galaxy clusters spotted something unsettling. The hot gas halos around these clusters showed a consistent velocity shift in the microwave background, an effect called the kinematic Sunyaev-Zeldovich KSZ effect. The clusters weren't just drifting randomly with the universe's expansion. They were all moving together like leaves caught in a hidden river. Follow-up studies using massive datasets like those from the Planck satellite confirmed the motion extended much farther than expected, billions of light years across, toward a point in the sky between the constellations Centaurus and Vela. The leading explanation, a gravitational titan lurking in the unobservable universe, beyond our cosmic horizon. The 14 billion light-year limit set by the age of the universe, there could be a supermassive concentration of matter, its gravity warping spacetime enough to pull entire galaxy clusters toward it. Simulations suggest such structures could form if cosmic inflation, the universe's explosive early growth, wasn't perfectly uniform. Imagine a tapestry with an uneven weave, some regions denser, others sparse. If a supervoid or a massive cluster of galaxies lies just out of sight, its gravitational influence might still reach us like a shadow stretching across a wall. But there's a catch. The standard model of cosmology assumes the universe is homogeneous on large scales, no preferred direction, no unseen giants yanking at the fabric of reality. Dark flow challenges that. Some critics argue it's a measurement error, a distortion caused by incomplete data or local peculiarities. Others propose wilder ideas like the multiverse. If our universe is a bubble among countless others in an eternally inflating cosmos, perhaps dark flow is the imprint of a neighboring bubble brushing against ours, its gravity leaking through the barrier between worlds. The hunt for answers continues. Upcoming surveys like the Euclid Space Telescope will map galaxy motions in unprecedented detail, probing whether the flow persists at even greater distances. If it does, we may need to rewrite our cosmic playbook. Either way, dark flow forces us to confront a humbling truth. The universe we see might just be the tip of an iceberg whose depths we'll never fully fathom. Imagine a star cheating death, blown apart by the violence of a supernova, yet somehow clinging to existence, now hurtling through space at unfathomable speeds. These are zombie stars, cosmic survivors that endure the unimaginable. Take LP40-365, a rogue stellar fragment racing through the Milky Way at almost 2 million miles per hour, fast enough to escape our galaxy entirely. Its secret, this wasn't just any explosion. It was a partial supernova, a detonation powerful enough to fling the star into the void but somehow leave it intact, a shattered yet still shining relic of its former self. What makes LP40-365 so bizarre isn't just its speed, it's what it's made of. Most stars are predominantly hydrogen and helium, the universe's default building blocks. But this zombie star's atmosphere is laced with neon, oxygen, and heavy metals like magnesium, elements typically forged in the heart of supernova. It's as if the star skinned itself alive in the explosion, exposing layers that should have been buried deep in its core. The explanation, a runaway thermonuclear reaction, one violent enough to strip away the star's outer layers and propel the remaining core like a cosmic cannonball, yet calibrated just precisely enough to avoid total annihilation. This isn't a fluke. Other zombie stars like SDSS Joan 2408.46 plus 22471 sport similarly bizarre compositions and extreme velocities. Many are what astronomers call hypervelocity stars, ejected from their home systems with enough kinetic energy to defy galactic gravity. Some might even be the remnants of white dwarf collisions, stellar partners that spiraled too close, triggering a supernova that obliterated one while flinging the other into the abyss. But the real mystery lies in the how. Supernovae are supposed to be final acts, the explosive deaths of stars that leave behind neutron stars, black holes, or nothing at all. Yet zombie stars like LP40-365 suggest there's a middle ground, a catastrophic yet incomplete destruction physics hasn't fully mapped. Some theories point to Type IX supernova, a weaker cousin of the standard white dwarf explosions, where the star doesn't fully detonate but instead suffers a partial disruption. Think of it as a bomb with a faulty fuse, enough to blast the star into exile, but not enough to erase it completely. The implications stretch beyond these stellar oddities. Zombie stars serve as cosmic forensic evidence, their trajectories and compositions revealing clues about the supernova that birthed them. By studying their paths backward, astronomers can trace them to ancient stellar neighborhoods, reconstructing the explosions that sent them flying. Their heavy elements spilled into space during their violent escapes might even seed future generations of stars and planets with the building blocks of life. Yet the most haunting question remains: how many more are out there? Current surveys, like those from the Gaia spacecraft, are uncovering dozens of these hypervelocity fugitives, each with its own story of survival. Some might be lone wanderers, others could hint at unseen companions, black holes or neutron stars lurking in the dark, the silent partners in their explosive escapes. Every zombie star we find is a reminder that the universe's violence is as precise as it is chaotic, capable of destruction and deliverance in the same breath. And as they streak across the cosmos, they leave behind a trail of light and questions burning brighter than ever. For decades, a shadow has circled Earth, not in the realm of science, but in the fevered imaginations of conspiracy theorists. They call it the Black Knight satellite, an alien probe allegedly orbiting our planet for 13,000 years, watching us with unknowable purpose. The legend took root in the 1950s when newspapers misquoted a scientist's speculation about strange radio signals as evidence of an extraterrestrial object. Soon, grainy photographs and out-of-context NASA audio clips fueled the myth, spinning tales of an ancient machine lurking in the void. But strip away the hype, and the truth is far simpler and far stranger than fiction. Start with the infamous photograph of the Black Knight, often touted as proof. That twisted, angular shape hanging against the curve of Earth. It's not an alien artifact, it's a thermal blanket. In 1998, astronauts on the ISS accidentally lost one during a spacewalk, and the lightweight debris quickly assumed a slow, tumbling orbit. Conspiracy sites latched onto images of it, ignoring the mundane explanation in favor of something more sensational. Orbital mechanics further demolished the myth. Any object left in low Earth orbit for millennia would have succumbed to atmospheric drag long ago, burning up like countless spent rocket boosters and dead satellites. The idea of a 13,000-year-old satellite defies basic physics unless, of course, aliens have mastered the art of perpetual motion. Then there's the radio signal at the heart of the legend. In 1899, Nikola Tesla picked up rhythmic pulses he couldn't explain, later interpreted by UFO enthusiasts as a transmission from the Black Knight. In reality, Tesla was likely detecting pulsars, neutron stars emitting regular radio bursts decades before their official discovery. The patterns he heard weren't alien Morse code, they were the natural heartbeat of the cosmos, a phenomenon we now understand well. Yet the myth persists, even bleeding into pop culture. The Black Knight has appeared in comic books, TV shows, and blockbuster films, its legend growing with each retelling. That's the irony of cosmic mysteries. Sometimes the stories we invent are more captivating than the science we uncover. In the end, the Black Knight satellite isn't evidence of extraterrestrial watchers. It's a mirror reflecting our timeless desire to believe that something, anything out there is looking back. And in that, it reveals more about us than it ever could about the stars. From the ghostly grip of dark matter to the violent churn of quantum foam, These 25 cosmic mysteries don't just defy explanation, they shatter our assumptions about reality itself. Each one is a doorway into the unknown, forcing us to question the very foundations of physics, time, and existence. Why does the universe expand faster than it should? What lurks in the voids between galaxies? Are we alone, or is the silence of the cosmos a puzzle we haven't yet solved? These aren't just gaps in human knowledge, they're invitations to rethink everything we thought was certain. Consider how much has already changed. A century ago, we believed the Milky Way was the entire universe. Now we know it's just one among trillions, adrift in a sea of dark energy, woven together by invisible threads of dark matter. We've discovered planets orbiting dead stars, black holes defying entropy, and anomalies in the cosmic microwave background that hint at realities beyond our own. Every mystery we've explored, from the wow signal's fleeting whisper to the Great Attractor's relentless pull, reveals how little we truly understand. And that's the thrill of it. Science isn't about having all the answers. It's about chasing the questions that keep us up at night. So what's next? Maybe the James Webb Telescope will spot a galaxy where none should exist. Perhaps a neutrino detector will catch a particle moving backward in time. Or one day, a radio signal will crackle through the void, and this time we'll know it's no accident. The universe is vast, strange, and far from finished with its surprises. And that's why we keep looking, because every discovery, every enigma, rewrites the story of our place in the cosmos. Now it's your turn. Which of these mysteries haunts your imagination? Is it the rogue black holes drifting unseen through our galaxy, or the chilling possibility of a multiverse brushing against our own? Drop your favorite in the comments, and let's keep the conversation as infinite as the stars. After all, the greatest discoveries start with a single question: what if? And in a universe this wild, the next revelation could be just beyond the next telescope's gaze. Stay curious, the void is listening.